All right, so we're in the home stretch. We're almost there. We're getting close. The final is coming up in a week and a half. This week we have our last few lectures on Friday. Immediately after class, we'll do a little bit of review. Probably we'll start before class ends. We'll just have to see how far we get. So just some really basic stuff. Here are some antiderivatives, indefinite integrals. We've talked about these before, so I'm not going to go over them again today, because we have a lot to talk about today. So we've learned about integration, and we saw that integration has this sort of relationship with derivatives. And in particular, integration and antiderivatives are very closely related. And we may ask the question, well, okay, sure we can do this thing called integration, but is it useful for anything? And in fact, it is useful. In the history of mathematics, if you look at it, we always teach derivatives before we teach integration. But in fact, historically, integration came first by about 2,000 years. The ideas behind integration date back to the ancient Greeks. So integration has a richer history, and certainly I think has more interesting problems. And the first thing we saw was that integration can find area. Now this is not a surprise, because that's how we first thought about integration. We thought about these Riemann sums. What's the total underneath the curve? Now the only thing about area that we have to be careful, of course, is the fact that previously when we thought about integration, we didn't care whether area was positive or negative. So we could say this is positive area, this is negative area. We're not going to guarantee that everything is positive. So the really only difference here about finding area is we're just going to make sure everything stays positive. So in particular, if I have two curves, a function f of x and a function g of x, and the function f of x is always on top in the interval between a and b, then the area between the curves f of x and g of x, between x equals a and x equals b, is the integral from a to b of the quantity f of x minus g of x dx. Now what's the intuition behind this? Well, the intuition is I have these two curves, f of x and g of x. F of x is larger, and so it's on top. And I'm going from a to b. And the best way to think about how to set up your integrations is to think about, okay, I'm going to take small little slices and figure out what's happening in each slice and combine them together. That's sort of going to be the theme for today. I'm going to say that 3 or 4 times today. Take little slices, add them all up. So in this case, I'm taking a little slice here. I'm taking these vertical slices up and down. So if I look at such a slice, I can say, well, what's the width? The width is how much I'm changing here in the x direction, and we'll call that width dx. And the height is how much I change in the y direction, and that's simply the difference between the two curves, f of x minus g of x. And because f of x is larger than g of x, f of x minus g of x is positive. So that if I look at the area of one of my slices, it's f of x minus g of x times dx, the height times the width. Now that's the area of one slice. Of course, I don't want the area of just one little tiny slice. I want the area of all of them, and so I add it up. And that's what integration is. Integration is adding all the little pieces up together. All right, so that's how we find the area. Now, we don't just have to take the integration with respect to x. I could also say that I have x equals f of y is greater than x equals g of y for a less than or equal to y less than or equal to b. So in this case, I have a picture where I have a function over here. Here's my x is f of y. And I have a function over here. Here's my x equals g of y. And to say that f of y is greater than or equal to g of y just means that if I look at this picture, on the right-hand side is f, on the left-hand side is g. And this is between y equals a to y equals b. So again, I can find the area in between the curves here. Now the only difference is instead of taking vertical slices, I take horizontal slices. And I say, okay, well, how big is a slice? Well, now the height is dy. The width is now the difference between the functions, f of y minus g of y. So that the area in a little slice is f of y minus g of y dy. The width times the height. And then I just need to add up all the little slices together. Integrate from a to b. And in fact, you should notice that these look amazingly similar to each other because they are the exact same idea. There's no real difference here. Sometimes, depending upon your function, it's easier to take the integral with respect to x. Sometimes it's easier to integrate with respect to y. Sometimes it doesn't really matter. You can do it with respect to either, and you'll get the same answer. Okay. So that's how we go about doing it. I guess I should also point out that if you don't like f of x minus g of x, a real basic way to think of it is the top minus the bottom. Just whatever one is on the top, subtract whatever one's on the bottom. In this case, f of y minus g of y, you can also think of this as the right minus the left. Just whichever one is the larger value, subtract whichever one is the lower value. Now, basically, since this is so easy, how can we trick you up on these kinds of questions? Not that that's what we'd want to do, but, we'd like to ask some questions that make it more interesting than just doing some basic integration. So oftentimes we'll ask for area, but maybe we won't tell you which one's on top. Well, okay, then you have to figure it out. Or sometimes we might be even a little bit more cruel and say, okay, find the area between, okay, y equals cosine x and y equals sine x for 0 less than or equal to x less than or equal to pi halves. Now, this seems very simple. Why does it that there will be any difficulty? Well, let's try to graph these functions. So y equals cosine x looks like the following. So here's 0, here's pi halves. It does this. Y equals sine x, on the other hand, looks something like this. So when I'm asking for the area between y equals cosine x and y equals sine x, I'm asking for this area plus this area. Now, where's our problem? Well, our problem is that we don't have f bigger than or equal to g for all points on the interval. See, there's a difference here. Somehow in between, something happens where beforehand, on the top is the cosine, and then over here, cosine's on the bottom. And on the bottom's the sine originally, but now the sine's on top. So the function which is on top changes. Well, we can fix that. Or I shouldn't say we can fix that, but we can handle that. And the way to handle it is simply to say, well, look, instead of trying to break it up and do the instead of trying to do the integral in just one fell swoop, let's chop in half. I'll do the integral into parts. In this case, 2 parts. The part from 0 to wherever this point is, and the part from wherever this point is to pi halves. Because in each one of those parts, I have a very simple way to do it. I just apply this technique. Now, of course, I have to figure out where do I split. So how do I figure out where I split? Well, I split where the curves intersect. So I say, okay, well, when does cosine x equal sine x? Now, hopefully, we all know an angle where cosine x equals sine x between 0 and pi halves. In fact, it's halfway in between at pi fourths. At pi fourths, they're both equal to root 2 over 2. If you didn't know that, you could have divided both sides by, say, cosine. Then you get 1 equals tangent of x. Then you could say x equals the arctangent of 1. And hopefully by now, we all know the arctangent of 1 is pi fourths. If you don't, it's on the sheet for the final. Useful thing to know. That might be a nice thing to know. Okay. So what do? Well, simply now our area will be the integral from 0 up to pi fourths of the top, cosine, minus the bottom, sine, plus the integral from pi fourths to pi halves, the top, which is now sine, minus the bottom, which is now the cosine. Now, I'm going to save myself some work and claim that there's symmetry, and that this area between pi fourths and pi halves is the exact same as this area between 0 and pi fourths. If you didn't see it, you can go through and do the whole thing. You'll get the same answer either way. So in other words, I'm saying that these two areas are the same. So this is 2 times the integral of 0 to pi fourths times cosine x minus sine x. Okay, now, lucky for us, cosine and sine are nice functions. So nice that we actually know how to integrate. They're on our list. They're on our very, very short list. So this is 2 And what's the integral of cosine? The integral of cosine is sine. So this is 2 sine. What's the integral of sine? The integral of sine is negative cosine. So the integral of negative sine will become actually a positive cosine. Then we evaluate from 0 to pi fourths. So that's 2 times root 2 over 2 plus root 2 over 2 minus 2 times 0 plus 1. So we end up with 2 root 2 minus 2. Okay? All right. So a lot of the problems, it really just boils down to find how the curves intersect, how they play around with each other, and then, if necessary, break it into parts. So, for instance, a problem in the book, let me just write down these curves. Well, you have a curve y equals 8x. You have another curve y equals x. This is not drawn to scale, but you have a curve y equals 8 over x squared. And you're asked to find the area that these three curves bound. Well, there's only one area that these three curves bound together. That's finite. So in other words, they're asking you to find this area here. So how can we do it? Well, the trick is just to realize that on doing these kinds of problems, I'm always taking top minus bottom. So here, I see that top minus the bottom is 8x minus x. And it's still 8x minus x. But then somehow at this point, it changes. So that I go, instead of going from 8x minus x, I now go to this curve, which is the 8 over x squared curve minus x. So the best way to do these problems is just sort of chop it into pieces. Say, well, look, from wherever this point is, and it's easy to see this point is at 0, to wherever this point is, I'll have top minus bottom 8x minus x. Then from wherever this is to wherever this is, I'll have the 8 over x squared minus x. So what's the steps? Well, steps are you draw a picture, you get a grasp of the situation. And then you can sit down and you say, well, where are my important points? The intersection points. Because these intersection points are the points that are going to determine your boundaries, where you integrate from where to where. So for instance, x and 8x both cross the origin. So it's easy to see that this point is at 0. But maybe this point's not so easy. So I may ask, well, when does 8x, which is this line, equal 8 over x squared? Well, you can rearrange that. That's the same as saying x cubed equals 1. Now we're saying, okay, I can do that one. X cubed equals 1 says that x is at 1. So now my first integral will be from 0 to 1, 8x minus x. Okay, how about here? Well, that says I need to figure out where the intersection is when x equals 8 over x squared. Well, that's the same as saying x cubed equals 8. And so that's at x equals 2. So my second integral will be from 1 to 2. So I'm finding the area first here, find the area here, and then I just add the two areas together. All right. So one problem we talked about last time, see how far we can get in 5 minutes. Well, so we had the problem, find the area between y equals 2 absolute value of x and y equals 9 plus 5x minus 2x squared. I actually haven't done this one all the way through, so hopefully it doesn't get too bad. But the picture here is we have this function 2 absolute value of x, and then we have some sort of upside down parabola. So the picture, roughly speaking, looks like this. And we're asked to find this area here, the area between them. Now, the hard thing, of course, whenever dealing with absolute values is that absolute values are very difficult to deal with because we don't like to try to integrate absolute values. But that's not such a big deal. Because really what I can think of this is I can think of it, well, it's really like the line y equals 2x on this side and y equals negative 2x on this side. So in other words, whenever I have whenever I have an absolute value function, I can turn it into a piecewise function. I can break it into parts. And each part is very simple. Negative 2x and 2x. Both of them are easy. They don't have absolute values. And now I feel much more comfortable having them hang around. So suppose I want to find the intersection. So if I want to find this point of intersection, well, that's when 9 plus 5x minus 2x squared is equal to negative 2x, which would be the case when the two absolute value of x, when I'm looking at x less than 0, which is where my intersection is going to occur on this side. Well, let's see. How can I rearrange this? I can rearrange this. This is the same as saying 2x squared minus 7x minus 9 is equal to 0. And if you're really good at factoring, and if you're not, you can not factor. You can use the quadratic equation. But if you're really good at factoring, you'll see that, lo and behold, this factors into x plus 1 times 2x minus 9. You can check 2x squared, and you get minus 9x plus 2x is minus 7x, and minus 9. So you get x equals negative 1, or x equals 9/2. Now, I'm looking for the intersection where x is less than 0. So I'm not looking for the 9/2 point, because I'm looking for where x is less than 0. That tells me now that I'm looking for that point, negative 1. Now, that's my first intersection point. Now, the other intersection point is very similar. 9 plus 5x minus 2x squared equals 2x. Now I'm looking for the intersection where x is greater than 0. In that case, I think of two absolute value of x as simply 2x. Again, I can rearrange this. This is the same as saying 2x squared minus 3x minus 9 equals 0. And again, if you're really good at factoring, if not, use the quadratic formula, you'll see that this factors into x minus 3, 2x plus 3. You can check. 2x squared plus 3x minus 6x is negative 3x, and then minus 9. So again, the roots are at 3, negative 3/2, but since I'm looking for my positive roots, I can throw out the negative 3/2, and now, lo and behold, I found it. It's at 3. So I found my points of intersection. They are negative 1 and 3. Now I need to find the area. So there's a couple ways to find the area. Again, just really it boils down to finding the integral from negative 1 to 3 of the top, which is 9 plus 5x minus 2x squared, minus the bottom, which is 2 absolute value of x, dx. Well, that's the integral from negative 1 to 3, because I can break this up. So now I know this is what I'm after. So whatever I use to figure out what this is, as long as I get the number, it doesn't really matter what I use to get there, and then I'm fine. OK, so I have this integral minus the integral of negative 1 to 3, 2 absolute value of x dx. Which integral do you want to tackle first? Let's do this one. Let's do this one because that one we can cheat. It's not cheating, but we can be a little bit sneaky and actually avoid integration. Or I should say avoid antiderivatives, because we can say, well, look, I know what that integral represents. That integral represents the area between that curve and the x-axis. So I come over here and I say, OK, so I really can think of it as this triangle plus this triangle. So instead of actually going and doing the integration, I'll just say, well, let's just find the area of those triangles. It's the same number. I just need the number. Well, my curve says I'm taking 2 times absolute value of x. So this is height 2. This is height 6. So I take whatever 2 times absolute value, in this case, plug in negative 1, I get 2. So what's the area of a triangle that has base 1, height 2? Well, half base height. So this area is 1. What's the area of a triangle that has base 3, height 6? Well, a half times base times the height. So that has area 9. So that when you go through and you work out this integral, It's the little triangle, which has area 1, plus the big triangle, which has area, I said 9. So this is 10. So this is 10. Okay. Now let's go and do this integral. So -1 to 3, and then this is, oh, actually, we're ready to take the integral. So this is 9x plus 5/2 x squared minus 2/3 x cubed. Evaluate that from -1 to 3. And then, of course, we have this minus 10 on the end. Okay, so we get 27. 3 squared times 5/2 is 45/2. 3 cubed is 27 times -2/3 is -18. Subtract -9 plus 5/2. The -1 cubed is negative times -2/3 is plus 2/3. And then all that subtract 10 on the end. Okay, let's see how far we can get. So I have 45/2 minus 5/2. All right, let me see if we can put it up here. Oh, I don't want to erase that. We'll put it here. Okay, so first off, let's just handle some. 27 subtract 18 is 9. Then I have a plus 9, and then I have a minus 10. So I have a 9 plus a 9 minus 10 is 8. Okay, so that takes care of this, and that. 45/2 minus 5/2 is 40/2. 40/2 is another way to say 20. Okay, so that takes care of the 45/2 and the minus 5/2. And then finally I have minus 2/3. That takes care of the 2/3. Okay, so now I've accounted for everything. So you get 28 minus 2/3, but you can also put this into fraction. 28 is the same as 84/3 minus 2/3. So you get 82/3. Hopefully, unless I made some mistake. And this is when you leave your time on the final so you can go through and say, okay, double check your arithmetic. But I know I'd get a lot of partial credit for this. Okay, so there's a very simple application of integrals. And this is not a very surprising application because that's how we started thinking about integration, was thinking in terms of area. So let's try to find some other applications for integration. So the big one for this week, and the one we'll spend a lot of time on Wednesday and Friday, is volumes. So how do we go about finding the volume of a three-dimensional object? So I have some sort of a three-dimensional blob, some weird shape. And I want to find the volume of this shape. Well, one way I can think of it is I go back and I say, well, how did I find area? The way I found area was I said, I know, I'll just cut it up into little tiny pieces. And each piece I understand. Then I'll add up all the pieces together. So we're going to do the exact same thing. Well, when we take pieces, now we're not going to find our pieces are little areas. Our pieces are going to be little tiny volumes. So what I'm going to do is I'm going to take this volume, and I'm going to chop it. And I chop it, and I see what happens. So I've chopped my volume up. And lo and behold, when I take a slice, let's say, I've got to put some coordinates on here. Suppose this is the y direction. Here's the x direction. Here's the z direction. So I take a slice as I move in the y direction. And I look at this little piece. Now, when I pull that slice out and I examine it more closely, what do I see? Well, I see something that looks like this. It has some sort of an area. I'll call it the area of y, which is the area when I take the slice at y. So here's y. Plus, I didn't take this infinitely thin slice. I took a slice with just a little tiny bit of thickness. A very small thickness, a thickness of dy. Now, what is the area? Sorry. what is the volume of this? Well, to find the volume, imagine, it's like finding the volume of a cylinder. How do you find the volume of a cylinder? Well, you take the pi r squared times the height. It's the same basic thing. If you have an object where it has the same shape straight up and down, the way you find the volume of that is you take the area of your base times your height. So that's the volume of that little tiny slice. Okay? So I really should say that this is a sort of a thick slice I'm taking here. So I know the volume of one slice. Well, once I know the volume of one slice, how do I find the total volume? Well, very simple. I add up all the slices. So here's the volume. And I should say what A of y. A of y equals the cross-section. The area of the cross-section. Taken at y. So just chop it up into little tiny volumes, add up all the volumes together, lo and behold, we get this volume out. Okay. That's it. That's how we find volume. Very, very simple. And yet, it leads to so many cool problems. Woohoo! As you'll see. By the way, you really should be able to start your practice finals now. By the end of today, you should be able to answer 9 out of 10 on all the practice finals. Hopefully, before the end of today, you could answer at least 8 out of 10 or 9 out of 10. Okay, so that's how we find volume. Now, I talk about taking a slice here as we vary y. Of course, we could also take different slices. We could take slices in different directions. So, for instance, let me see. I know I'm going to be in trouble next quarter. I'm teaching multivariable calculus. And so the only requisite for being a teacher for multivariable calculus is you have to be able to draw three-dimensional pictures. Unfortunately, I fail miserably in that regard. Okay, let's see. So suppose I take as my shape not just anything. Let's use something very simple. A wedge. And I wanted to find the shape of this wedge. So suppose this was our goal. How would we go about it? Well, we'd go about by taking slices. Now, we can actually go about taking slices in lots of different ways. So let's label this as x, y, and z. Now, one way that I can take slices is I could take them with respect to x. So if I take a slice with respect to x, so that's, in other words, I'm moving my slicerometer back and forth along the x direction. When I take a slice, what do I get? Okay, I need more colors here. I'll use red. Take a slice in the x direction, the shape I get is this rectangle. And then the area is simply the area of this rectangle. And of course, as I move along, so at the very extreme end here at x equals 6, my rectangle is just simply a line, and I move up further and further along. It gets bigger and bigger. The width is always 4, and as I go up, the height increases linearly until I get to 2. And so I could sit down and I could figure out what the areas of each one of those cross sections, and I'd find the total volume. I could also, of course, take slices in a different direction. I could also take slices with respect to z. Okay. Now, if I take a slice with respect to z, now my cross sections are, again, they're rectangles, but they're different kinds of rectangles. So I'm moving up and down as I take my cross sections now. So at z equals 2, my cross sections again align. Then as I move down, I get rectangles which are getting bigger and bigger and bigger. until I get to the very bottom. Now, of course, there's an even much simpler way to do all this problem, where we don't even have to do any integration. How do we find the volume? Well, what if I take a cross-section with respect to y? What do I get? If I take a cross-section with respect to y, I'm always going to get the exact same shape. I'm always going to get a triangle which has length 2 here and length 6 here. What's the area of this cross-section? Yeah, the area of this cross-section with respect to y is 6. Okay, so where can y vary between? Well, y can go from 0 up to 4. So the volume is the integral from 0 to 4, a of y dy, which, of course, is the integral from 0 to 4 of 6. Well, that's pretty easy to figure out. It's 24. So the moral of the story is that you can take cross-sections in different directions. So here, I could also say that the volume is also equal to the integral. There might be different bounds, c to d, the area of the cross-section with respect to x dx. It might be, again, different bounds, e to f. Whatever the right bounds are for your cross-sections, a to z to z. Just whatever direction is helpful for you to do cross-sections. And we'll do more of this on Wednesday, so I don't want to dwell too much on this today. But let's just do one very, very simple example. Suppose I take any shape. Let's make it something I can draw. Suppose I take any shape that I can reasonably draw. Okay? And this is down here in the xy plane. And then I pick a point somewhere up here, which has distance h from the xy plane. So in other words, if I were to drop straight down, it'd be length h. Okay? That's what I mean by this distance. Now, what I'm going to do is I'm going to form a three-dimensional shape. And the way I'm going to form this three-dimensional shape is essentially I'm going to take this, and I'm just going to take this shape and just shrink it down to that point in a nice, straight, linear kind of fashion. Constantly shrinking it down so it all looks the same. So we've already seen examples of this. For instance, one very simple example is the cone, where I start here with a circle, then I pick a point above it, directly above it, and I get this shape. Now, what's the volume of a cone? Well, it's 1/3 pi r squared h. We've seen this one a few times. Another example, which we've seen on a midterm, and probably on some homework as well, is I can start with a square on the bottom. And I pick a point above it. So I form a pyramid. Suppose this length is b. Again, this distance here is h. Do we know what the volume is? Well, it's 1/3 b squared h. And in fact, we're going to show here that suppose that this part, the area of this is equal to b. Then the volume of this shape is 1/3 times whatever b is times your height. And in fact, that's the pattern here. Notice the area of a circle on the very bottom is your pi r squared. 1/3 pi r squared h. The area of the square on the very bottom is b squared. 1/3 b squared h. And you'll see they both fit this pattern. So we can do another shape very easy. Suppose I say, take my three axes, x, y, z, and I'm going to just make a nice little tetrahedral shape here. So it's a three-dimensional solid where I go from 0, 0, 0 up to these 3 points on the three axes, A, B, and C. So this has length A, this has length B, this has length C. What's the volume of this shape if you were to apply this rule? Well, what's the area of the base? What's the area of this triangle on the bottom? Yeah, it's 1/2 base times height, or 1/2 a times b. So that's the area of the base. Then I times that by 1/3 times the area of the height. In this case, the height is c, so it's 1/6 ABC. Okay, so let's see if we can prove that 1/3 base height. Well, how do we go about proving it? We take cross sections. So what I do is I look at this and I say, all right, I come up and I take myself a cross section here. And what shape do I get? Well, it's the same shape down on the bottom. It has the exact same shape. The only difference, of course, is that I've scaled it down. So the question is, well, how much should I scale it down? If I know how much I've scaled down, then I know exactly how much the area is of this compared to that, and I'm good to go. So suppose, for convenience, let us suppose we label this as height 0, this as height h, and let's see, is that convenient? Yeah, it is convenient. Okay. And this is a height y. So that's where I'm taking my cross section. So I'm being a physicist, where I just assign my direction wherever it's convenient. This is okay. All right? Well, how do we find the area? So let's say this is the area of y, is the area of that cross section. Then the area at height y divided by the area of the base is equal to the ratio of the y length, which is how high I go to take my slice, divided by the h length, quantity squared. And the reason I put a square here is think about how do you get area. Area is the product of two dimensions, length and width. And length is just the product of one dimension. So this is just to make it more comparable in terms of dimensions. So the area of y is the base over h squared times y squared. Okay, now I'm going to add up. So I integrate from 0 up to h, because for my picture here, I start at 0, and I go to h, take all my cross sections, and that covers the whole shape. A of y dy. Okay, that's the integral from 0 to h. B divided by h squared times y squared dy. Now, the b over h squared is a constant, so that comes out. And then y squared dy, well, that's very easy for us to integrate. That's 1/3 y cubed, evaluated from 0 up to h. So I get b over h squared times 1/3 times h cubed minus 0. The 0 doesn't do anything. And so finally, we have 2 h's on the bottom, 3 h's on top. So I simplify, and I'm left with 1/3 b h. All right. So there's an example. So there's how we can find volume. And we're going to do a lot more of these on Wednesday and Friday. So let's do something else that we can do with integration. All right, suppose I'm trying to find mass. And in particular, I'm trying to find the mass of a rod. Now, what do I know about this rod? Well, I have some information about it. I know the density of the rod. Let's say it's rho of x equals kilograms per meter. So in other words, I have this rod here. And if I go out distance x, I know how dense that is. So it might be that when I made this rod, I used varying different kinds of metals or varying processes, so that at some parts of the rod, the metal is very thick, very dense, very heavy metal. Some parts, it's a different kind of metal, very light. So, of course, how do you find it? If they were all the exact same density, very easy. Just take the length times by density, and I'm done. But it may not be constant density. So, specific example, suppose my density is 1 plus 2 times x times 2 minus x, and 0 less than or equal to x less than or equal to 2. This says that essentially, if you look at the density, that per meter, and there's a 2-meter rod, at the endpoints 0 and 2, it only has density 1. And what happens is as you move closer and closer to the middle, your density increases, so much so that at the middle point, at x equals 1, which is halfway in between, your density gets all the way up to 3. So it's a rod with varying density. All right, so how do we do it? Well, we do the exact same thing we do for every problem with integration. Namely, we take a little tiny sliver. So imagine, if you will, I'm going to take my rod, and I'm just going to cut a little tiny piece of it out. And say, OK, look at this little slice. Well, because I'm looking at such a tiny slice, now I don't need to think of my rod as having varying density. I just say, well, what's the density at that point? The density at that point is simply rho x. And because my slice is so small, it's going to essentially be a constant now. All right, well, that's the density. Well, how big is that piece? Well, the width of the piece, or the length of that piece, is dx. So if I take the density, which is I essentially have constant over that little tiny piece, times by the width of that piece, then this is the weight of that little piece. So here's the weight, or I should say mass, of a small slice. All right, so I know how to find the mass of a slice. How do I find the total mass? Well, I add them all up. Once I know the mass of a little bit, to find the mass of everything, I just add them all together. That's what integration is. Break stuff up into small pieces, figure out what's happening with each piece, add it all together. So in this case, if I want to find the mass here, I get that the mass will be the integral from 0 to 2 of the density function. OK, well, that's the integral from 0 to 2. Let me move it up here a little bit. And if I expand, this is 1 plus 4x minus 2x squared dx. Just one of our rules for helping us to do integration is, well, if you don't know what to do, you work on it. One of the things you can do, obviously, to simplify integrals is to expand out. That's what I did, it's just to expand out. Because now I broke it into 3 pieces. Each piece is easy. The integral of 1 is x. The integral of 4x is 2x squared. And the integral of 2x squared is 2/3 x cubed. So now I can integrate. Very simple. Evaluate from 0 to 2. Notice how if I plug in x equals 0, I just get 0. So I really just need to plug in x equals 2. So that is 2 plus 8, which is 2 times 2 squared, minus 16/3, which is 2/3 times 2 cubed. 2 plus 8 is 16, which is 48/3. Minus 16/3 gives us 32/3. OK, so now I know the mass of that rod, 32/3 kilograms. All right, so that's one kind of density. Now we can do another kind of density. Here, the density was essentially linear. It's like, well, how do you find out how dense you are? We just look at how far you are along the rod. Sometimes, though, we might have a density function which deals with a slightly different kind of shape instead of having a rod. This comes up, for instance, when you're studying cities. So where do people like to live in a city? Well, what tends to happen in a city is that people like to live near downtown. Downtown is very vibrant. You know, they have the best hot dog stands in downtown. So it's a good place to live. And the further away you get from downtown, the less dense the population is, because everyone's trying to move in. So one way to model the city is to say, well, look, you can model the density of the city, or density of the population of the city, based upon how far away you are from the center. So the city has the densest population at the center, and then as you move further out from the center, it gets less and less dense. You're hitting the suburbs. You get green trees, et cetera, et cetera. So we might have that the density, let me put it as r, is, for instance, 5 over the square root 1 plus r squared, 1,000 people per square mile when, she's capital R, we are r miles out from the center. So the further off I move away from the center, the less dense I get. So it's, where do you see the skyscrapers? They're in the middle. Then as you move out from the middle, the skyscrapers get smaller and smaller because there's less and less density going on. So I might ask a question such as, okay, I know what the density is behaving like. It's behaving like this function. And I say, well, how many people live within 10 miles of the city center? By the way, this function, if you look at 5 over square root 1 plus r squared, it starts off at 5 and then it just sort of drops down. So it's a decreasing function. Okay, so we want to know how many people live within 10 miles of the city center. So again, essentially it's the same kind of density question. We have a density. It's a little bit different here because as I took slices here, really I just had a very thin rod. I just took a little tiny slice. Now when I come over to here and I take a slice, well, what's the best slice to take? Well, the best slice to take is I know this density is essentially constant when I fix r. So if I look at a fixed length r, where r is the distance from the center, then all the density on this whole circle all the way around is the exact same. So now instead of taking these little thin slices, I'm going to take slices which are going to be this little tiny annuli. I'm going to take these. These are going to be my slices. In some sense, you may wonder, well, why are we taking those slices? Well, what we're really after for, ultimately in this problem, is I'm going all the way out to 10, and I want to find how many people live in the city in that shaded region. So I have to find a way to split up. Because the way you do integration is you split up what you're trying to find into little pieces, and you split it up so that each little piece you understand well. And in particular, we want it to be so that each little piece is essentially, where is this fixed? Where is it constant? Well, it's constant on these circles. So you say, okay, I'm going to split it up into these little circles and figure out what's happening in each little tiny strip. Now, how big is this little shaded region here? Well, if I say r was to the inside here, and r plus a little change in r plus dr is all the way to the outside. One way I can figure out what's going on is I can take the difference in the area of the circles. So if I look at the area of the big circle, which is sort of the outside edge of the red, subtract the area of the little circle, which is the inside edge of the red, that's the area of this little thin red circle, thin red annulus. Now, this is pi r squared plus 2r dr. Oh, sorry, I should use a capital dr here. Plus dr squared minus pi r squared. And if you simplify this, this is simply 2 pi r dr plus pi dr quantity squared. Of course, whenever I think of, r dr, I'm reminded of the Simpsons when they said, well, what's the derivative of 1/3 r cubed? Do you remember what this one is? Why is it your favorite derivative? Well, the derivative would be r squared dr, or r dr r. R dr r, you know. It's a Simpsons episode. You should, okay, all right, maybe it's a generational thing. There was a great cartoon in my day. Okay, now the point here is that the dr squared is so tiny because it has dr. Dr is small, infinitesimally small. So if I square it, I get something super, super tiny. So that the area of this little tiny slice is 2 pi r dr. Now, so that's the area of the slice. Now, how many people live in that slice? Well, I need to know the density. It's this. So if I look at, so this is the area. Area times density is the number of people living in that little tiny section. So that's 2 pi r rho of r dr. And finally, what do I do to find the total? I add it up. Okay, so we'll finish this up next time, so since our time is up. So have a good day. I'll see you on Wednesday.